Dear viewers, today that is Renewable Energy Systems Laboratory. Last video we are seeing the experiment number 4 in standalone mode. Today we are going to see the experiment on performance assessment of grid connected systems of grid connected system of 1 kilowatt solar power system, right? Now in last video we are discussed about these PV based systems. The PV based system, which may be going to classified into grid connected and standalone. The standalone case we are already seen in last video. That video is uploaded in the Google in the YouTube channel, that is Renewable Energy Lab PV standalone 1 kilowatt peak power system. Right now, how it can be the grid connected system will be working. So this is the grid connected system, which may be further classified into directly connected to the grid utility by bimodal PV systems. This is a bimodal which have the so this is directly connected to the utility. There is no storage. So we are going to see this grid connected PV system, directly connected system without the storage. So in last video, that is the how to draw these MATLAB elements or MATLAB module blocks. Last video we are seen due to reduce the video size and the time limitation. If you want to drag and drop this block, I am also going to refer these two videos. These two videos having the each and every preliminary stage drag and drop, right, in the all the component, which means draw the circuit. Now we are after drawing the circuit, we are going to see the steps one by one. So this is the PV panel. I am going to double click that panel. Here, that is in earlier class I have seen, that is the 10 watts panel which is available. That is 19 panels which is connected in series for obtaining the 326 voltage for obtaining the peak value, that is 230 into root of 2, that is the root of 2, which may be going to arrive the peak voltage. For that purpose we are going to include these values. So now this is the one peak, that is 1 kilowatt. The overall values we are obtained that the 1 kilowatt 150 watts, 1 kilowatt 150 watts here we are obtained, right? Okay, right. So this is that the 1 kilowatt peak power at the wattage rating is that is 1 kilowatt, that is 1 kilowatt 150 watts, that is 1.15 kilowatts. Voltage is 336.3. Similarly, the 336.3 having a 3.42 amps, right? This is the maximum power point. Okay, right. So next, that is this is the forward blocking diode is used for to avoid the reverse power flow. Next, this is the current measurement. This is the DC voltage measurement. Again, this is the universal bridge. This universal bridge, this is the single phase. For 2 ohm bridge is selected. Snowball resistance is 1 e to the power value of 5. So we are selecting the MOSFET with the diode action. Okay. So now we need the some filtering action. We need the some filtering action. So that filter, which is we are going to use the LC filter. So this is the 50 e power minus 3, that is that the inductor value for the normal LC filter design for 1 kilowatt. So this is that the 25 e power minus 6. And also I am also tell some one thumb rule. Suppose if we are going to put here in that 50 microhenry, you may going to put the here of the value, that is 25 microfarad. That is Henry is that is millihenry. Here the microfarad, that is the half value. This is the thumb rule which may be worked in properly. And we need the damping resistance for the point, not one for damping resistance for regulating or to avoid the oscillations. So here I am going to measure the voltage, output AC voltage. Again, this is the AC source. AC source. What is the voltage? Output voltage is 230 RMS. So we need the peak voltage 230 into square root of 2. That is root 2. So we are obtained the 325 plus something. That is the voltage. Okay. So this is the another voltage. Now the major criteria is how we are going to connect this PV system, how we are going to connect this PV system or this inverter, which may be integrated into that grid or in the AC source. This is the big question mark. So why? That is the synchronization is very important. For that purpose, for this I have already told, that is this simulation is UG students beginners level. So for that purpose, that is simply I am also going to take the PLL, phase lock loop. I think you are studied the PLL in digital logics and discrete time systems, DSP based subject, and so much thing. So that is the minimum frequency is 45 hertz. And the maximum, that is the desired frequency is, which is 50 hertz. So this is the value I am also going to fix for the PLL. The output of the PLL, which may be going to given two values. One is that is the frequency. Another one is omega t, which means the theta, So this frequency, whenever the load is changes, this grid frequency also changes. If the grid frequency is changes, if the load is changes, then grid frequency is changes. If the grid frequency is changes, again we are measuring the voltage. And then fed this voltage into that the PLL. This PLL frequency we are going to feed into the sine wave generation of the modulating signal of this PWM. So this block is a PWM, sine PWM generator, sine wave pulse width modulation for single phase, that is a full bridge, that is inverter. So this is the frequency is carrier frequency. I am also giving simply 500 hertz. So this is 50 hertz system. So here this will produce the sine wave. This is the sine wave. How these values I am obtained. So the basic formula I have explained in the earlier video. Once again I am going to explain this thing. The basic is sine value, which is the sine of 2 pi f t into magnitude, which means the 230 RMS. So sine value, here the sine value 2 pi, that is the pi value I am also going to put here. Please see the calculations and other things. This is that the formula. Again you may going to see the what is this. This is the sine function which is available 2 pi. Next u of 4. U of 4 means that is the, what is this, the u of 4. This is I am also going to put the mux for the input of this MATLAB user defined function. That is the, this is the function, MATLAB function. So the fourth value, that is, this is the fourth value. So then only this is 1, again 2, again this one is a 3, this is the 4. So u of 4, here I am also going to fix sine 2 pi f t. This is the u of 4, this is the u of 4, this is the u of 4 is a frequency, and then which is multiplied with the del angle. This is the del angle. Next one is u of 3, one is the magnitude. Next, that is what is the phase displacement of this each value. So now I am also phase displacement, we are going to fix the value of 0, right? Value of the 0. So third value, which is the 0, I am also going to put, there is no phase displacement occur in the system. Okay, the next one is the magnitude. Magnitude is, we are going to fix the u multiplied by the u2. This u2 is the, here the constant. Again this constant, please see that with my cursor, whenever I am going to click this constant, which may be linked with this slide gain. Suppose I am going to change this gain value, the sine wave produced in this output function is varied. So this is the basic concept. So now I am integrating this grid through this PLL. Through this PLL, the output of the PLL is a frequency. I am also going to fit this frequency. Here I measure the output of the grid voltage, then modulating signal. What is the modulating signal? That is PWM output. Next to modulating signal. Both are we are going to compare whether the grid connected system is synchronized or not. Okay. Now I am going to run this system. Right. Now it can be running. Yes. So this is the system may be run. Now the system is compiling. It may it may going to start run. So that is a very slow point of, because for identifying the value I am also bringing a very high sample value 50 e minus of 0.7. So now at the time of for certain period I am also going to fix that, change the modulating signal, and how it can be output waveform is changed. Now we want to see that the what is the output voltage, what is that the output voltage. Now the frequency is fixed, that is the that is 50 hertz. Now I am also going to press, so double click this scope. So what is that output? So this is that the output, which may be nearly, that is 3 plus or 3 something. So that is the, this is the another one is the current, and another one is that the voltage which is available. Now I am also going to change this for 0.5. So 0.5, now it can be changed. So what is this, the next, that is the scope output. So this is the, again further the output values will also going to be changed. This will be disturbed, and then the output value will also going to be changed. How it can be realized? By seeing this value. What is this? That is the current drawn from that the PV panel will also going to reduce, and if the point is current is reduced from that this current value to that value, again it maybe reaches the high voltage. Please see this diagram. This is the PV based. If the current value is that is 3.4, that is 33 plus 6. Suppose it may be increases, that is the current may be increases, that is the voltage may be increases, and the current will be reduced. So the current is reduces, again the voltage is 379. So that is the same operation we are going to see. So not only for this, and we are going to verify, again we are going to upload, that is the maximize the signal. Again we are going to see the synchronization point. here. That is the point. That is the point. That is the synchronization point. Now I am going to wait for 2 or more steps. So that is the magnitude of the modulation index which is reduced. Based on this modulation index, the PWM pulse will be changed. We will see on a later, and also that is that the output voltage and the current will also be changed. So this is the point. But only the thing, you may change, it may control the injected current by del angle, but if the voltage is to be maintained. If the voltage is reduced, then we are not able to synchronize with the grid is not synchronized or connected to the grid. Okay, so that is very important thing we are going to be see. So that is the another point. Okay, now that is the point 4. I am also going to see the point 5 at the end. Okay, so the point 5 end. Now the system which may be end are in point 7, which is available. So now that is which is we are going to see this graph. See this graph. I am also going to expand these simulations and all. This is expanded. Please see the zero crossing point. So this is the zero crossing point, and you can see that the place. So that is modulating signal will be reduced. Again, see this pulse width, and here you may going to see this pulse width. Okay, so that is the thing, and you may see the synchronization point. This is the 0 point here, that is the 0 point, which may be exactly matched with the synchronization. Okay, and we are going to see the what is the magnitude of these two waves. See, so what is the pulse width? Here the pulse width is different compared with this pulse width. Based on this operation, similarly the current will be reduced, and that the increase that the voltage, that the maximum power point is changed. So this is the simple study for the grid connected PV system. The PV which may be synchronized with the grid by using the PLL, that is the phase lock loop. So that is the thing. The experiment. Now both the experiment which is completed for the experiment on performance assessment of grid connected and standalone 1 kilowatt peak power system, right? Okay.